Welcome to Chapter 9, Gas Power Systems. In Chapter 8, we talked about vapor power system. That is to say, when you have a thermal power plant, and how do you analyze the efficiency and everything. And now we move on to gas power system. What is gas power system? Probably everybody has one at least. For example, the gas engine in your car or the diesel engine in a car. So in this case, in this chapter, we're going to talk about the two engines. The first one is gas engine. And the second one we talk about is the diesel engine. For gas engine, the cycle has a name, it's called Otto cycle. And for diesel engine, it also has a name, it's just called diesel cycle. Okay, so now let's start from Otto cycle, which is for a gas engine. Okay, now let's take a look at this diagram. So first of all, you can see this is a gas engine, and usually it's a four-stroke engine. The combustion process is usually initiated by a spark, provided by the spark plug. Okay, so what are the four strokes? We have power stroke, exhaust stroke, intake stroke, and a compression stroke. Those are the four strokes. Let's start from the intake stroke right here. For a gas engine, the intake stroke will take in the air-fuel mixture, which is actually different from what the diesel engine takes in. So the piston will go down into a sucking air-fuel mixture. That's intake stroke. After intake stroke, we have to have a compression stroke. So piston will go up and compress the mixture to increase the temperature and the pressure of the mixture. And then after that is done, we go to power stroke. Power stroke actually has two steps. The first step is the combustion process. You provide a plug to initiate the combustion process. And also because you provide a plug, combustion process happens really, really fast. So it can complete within no time. It gives no time for the piston to move. So that's why usually for a gas engine, combustion happens at constant volume because it is so quick. It doesn't give time for the piston to move yet. And then after the combustion is completed, the gas will expand. So that is the second step within power stroke. That is an expansion process, pushing down the piston. So that is power stroke. And then the last stroke is exhaust stroke. So after you push the piston to the bottom, which we call bottom dead center, the piston will push up to push out the exhaust, and then move on to the intake stroke to suck in the new mixture. So those are the four strokes for a gas engine. Next, we need to convert the four strokes into thermodynamics. What we do first is let's take a look at the exhaust and intake strokes at the same time. In reality, what happens is you push out the exhaust and then you suck in the new mixture. The exhaust is hot and the new mixture you suck in is cold. This is what happens in reality. When we convert those two steps into thermodynamics, what we do is we combine those two steps into one single step. That is to say, we assume the hot exhaust will just sit inside the cylinder and it will do nothing but to stay there and lose heat. So it becomes the new cool mixture. So in thermodynamics, we combine exhaust and intake strokes into one single step. That is a heat loss process at constant volume since the piston doesn't move. Okay, so now you've noticed there's a significant change. In reality, it is a control volume because there's mass transfer. But when we convert those two steps into thermodynamics, it's actually a closed system because we assume there's no mass transfer. The hot exhaust will just sit inside and loses heat until it becomes the new cool mixture. Okay, so we combine exhaust and intake strokes into one single step. We call it process 223. And what is process 223? It is a heat loss process at constant volume. And after process 223, we move on to the compression stroke. And compression stroke is very easy. It is just process 324, and we call it isentropic compression. Isentropic compression. After 324, let's move on to the power stroke. Like we said, power stroke has two steps. The first step is the combustion process. We model combustion process as a heat addition process. You add heat to the gas at constant volume. We call it process 421. Why is it at constant volume? We already explained. Because you provide a plug, because you provide a spark, so combustion happens really fast. It gives the piston no time to move at all, so combustion completes in no time. There's no change in volume. And then after the combustion happens, which is process 421, what is going to happen is the expansion, and we call it process 122. It's isentropic expansion. So now we have the four steps in thermodynamics. 421, heat addition at constant volume. 122, isentropic expansion. 223, heat loss at constant volume. And process 324, compression, isentropic compression. It's very similar to what we learned in chapter 8 for gas power system. Do you remember for gas power system, what is 421? 421 is the boiler. That's where you gain heat, just the same as here. And then what is 122? 122 is the steam turbine. What happens in the steam turbine? Isentropic expansion, which is exactly the same as here now. And then what is 223 in a vapor power system is the condenser. That's where you lose heat. Same thing as here. 223 is heat loss at constant volume. And then 324 in a vapor power system is a pump. That's where you have isentropic compression, which is exactly the same as here. Okay, so the only difference here is the whole cycle is modeled as a closed system. Keep that in mind. So when you use first law of thermodynamics, you have to choose the short version. Okay, so now let's go back to our notes and sketch the four steps. We will sketch those four steps on two diagrams. They are P versus nu diagram and T versus S diagram. First of all, we do not need to sketch the vapor dome anymore because during any given time, the phase of the gas is always superheated. So everything will be to the right side of the vapor dome. That's why there's no need for us to sketch the vapor dome anymore. So let's start from 421. What is 421? 421 is the combustion process. And we said we model the combustion process as a heat addition process. You gain heat at constant volume. That's how you model process 421. So let's sketch process 421 on P versus nu diagram. So first of all, what is nu? Nu is specific volume, which is defined as volume over mass. For process 421, volume doesn't change. And then what about mass? Mass does not change either because it is a closed system. So volume doesn't change, mass doesn't change, then obviously nu doesn't change. That means for 421, the x-coordinate is constant. If the x-coordinate is constant, then 421 must be a vertical line. A vertical line. And next, up or down. What do you need to check? You need to check the y-coordinate. How does pressure change in 421? This is a heat addition process. You add energy into the system, so pressure must go up. So 421 must be vertical and up. Okay, next one, 122. After the combustion process, it is the expansion process. Expansion process. And we call it isentropic expansion. Those two steps combined together is called the power stroke. How do we sketch process 122 on a P versus nu diagram? First of all, it is an expansion process, so the x-coordinate, which is specific volume, will become bigger because volume becomes bigger. So that's why 122 will be to the right. The next one, because it expansion process pressure, the y-coordinate will become smaller, so it must go down. So 122 must go down and to the right. Okay, so now slightly curved 122. And make a note, it is an isentropic process, so entropy is equal to constant. Next, let's sketch process 223. What is process 223? 223 is the combined exhaust and intake strokes. We said we model these two strokes as one single step, that is a heat loss process at constant volume. And again, this is a constant volume process, so on a P versus nu diagram, it must be a vertical line. Next one, go up or down. This is a heat loss process. You lose energy, so the pressure, which is the y coordinate, must go down. So 223 vertical and go down. Okay, and then next one, 324. 324 is the compression stroke. And we call it isentropic compression. Okay, so now because it is a compression process, the x-coordinate nu must become smaller because volume becomes smaller. So 324 must move to the left. And then how does the y-coordinate pressure change? If it is a compression process, pressure must go up. So this process 324 must go up and to the left. So we connect 3 and 4 with a slight curve. And again, make a note, since 324 is isentropic, entropy S must be constant. So this is how you sketch the four strokes on a P versus nu diagram. Next, let's sketch everything on a T versus S diagram. Let's start from 421 again. This is a heat addition process at constant volume. Heat addition. Do you remember if you gain heat, you also gain entropy? And entropy is my x-coordinate. So actually my x-coordinate is becoming bigger. So move to the right. The next one, heat addition. So the y-coordinate temperature must go up. So 421 must go up and to the right. Go up and to the right. 421 slightly curved. And make a note, it is a constant volume process, so nu must be equal to constant. And then let's sketch 122, isentropic expansion. Isentropic, that means entropy, which is the x-coordinate, doesn't change, so it must be a vertical line. Go up or go down, we check the y-coordinate, which is temperature. Since this is an expansion process, temperature must go down. So 122 is vertical and down. Next, let's sketch 223. 223 is a heat loss process at constant volume. If you lose heat, you also lose entropy. So entropy, which is the x-coordinate, becomes smaller. So that's why 223 must go to the left. And next one, because this is a heat loss process, temperature, the y-coordinate must become smaller. So go down and to the left. Slightly curved, 223. And again, make a note, this is a constant volume process. So nu equal to constant. And then 324. 324 is isentropic compression. First of all, isentropic, so entropy, the x-coordinate must be constant. If the x-coordinate doesn't change, it must be vertical line. Next one, compression process, so temperature, the y-coordinate must be becoming bigger. So 324 vertical and go up. 324. Okay, so that's it. That's how you sketch the process on a T versus S diagram. Okay, so after the two diagrams, we're going to do the math. We're going to look for heat transfer and work for every single step. Let's start from 4 to 1 again. For process 4 to 1, which is heat addition, which is heat addition at constant volume. Okay, so we're looking for the work and heat transfer of this process. Let's start from work. The equation to calculate work is W421 equal to integral P dV, and the lower limit must be V4, the initial volume. Upper limit must be V1, the final volume. Okay, and now we know it is a constant volume process. So derivative volume, which is constant, must be 0. If dV is 0, then the whole thing must be 0. So for process 4 to 1, work is equal to 0. And usually the format we have is W4 to 1 divided by mass, and that must be equal to 0. Next, we look for heat transfer. We have work, and we're looking for heat transfer. Which equation goes to your mind? First law of thermodynamics. Very good. And be careful here. Which one should you choose? The long version or the short version? The short version is for a closed system, while the long version is for a control volume. What kind of system do we have here? We said when we convert the Otto cycle into thermodynamics, we said the whole thing would just be modeled as a closed system. So make sure you choose the short version of first law, which is Q minus W equal to delta E. And do not forget to add a subscript. And delta E is the change of total energy, which has three components just like before. The change of kinetic energy, the change of potential energy, and the change of internal energy. Okay, so we know work is equal to 0. Next, we can always neglect delta KE and delta PE. So Q421 per unit mass is equal to delta capital U over mass, so it becomes delta lowercase u. Delta means final minus initial. Final is number 1, initial is number 4, since this is process 421. Okay, so now this is our conclusion. Work 421 is equal to 0, and heat transfer for 421 is U1 minus U4. Okay, that's process 421. Next, we move to process 122. What is process 122? isentropic expansion. Which one you think is actually easier, heat transfer or work? Heat transfer must be easier. Why? Because heat transfer must be equal to zero. What is the reason? Because isentropic. Isentropic means the process must be adiabatic and reversible. And what does adiabatic mean? No heat transfer. So heat transfer for process 1 to 2 must be equal to 0. Now we have heat transfer. We're looking for work. What equation? First law again, and make sure you use the short one. The solution for work is W122 per unit mass, and it is equal to U1 minus U2. Okay, and then we move on to process 223. The name of process 223 is heat loss at constant volume again. So now, which one you think is easier to find? Work, obviously. W223 per unit mass must be equal to 0 because there's no changing volume. If there's no changing volume, derivative volume must be 0. So integral PDV must be 0. And now I have work. I'm looking for heat transfer. What equation? First law. First law. Make sure you use the short one again. Q223 over M equal to U2 minus U3. Actually, if you use first law, the solution should be U3 minus U2, and that will give you a negative solution. Just like before, we do not prefer a negative solution, so we switch U2 and U3. We use U2 minus U3 to make sure we always get a positive number. But you just have to remember, for process 223, it is a heat loss process. So even though your solution for Q223 is positive, keep that in mind. This is a heat loss process. Okay, and then the last one is process 324. This is isentropic compression process. And just like before, which one is easier? Must be heat transfer. Heat transfer must be equal to 0 because it is isentropic, and isentropic means it is adiabatic plus reversible. Adiabatic means no heat transfer. And now we have heat transfer, we're looking for work. Again, use first law of thermodynamics. W324 over M from first law, that is U4 minus U3. So now have you noticed the trend? When we were talking about vapor power system in chapter 8, everything, either heat transfer or work, was in the format of the difference of the two enthalpies. And now when we move on to chapter 9, gas power system, everything is just in the format of the difference of the two internal energies. And then we always use the bigger U minus the smaller u to make sure our solution is always positive. Okay, so after each step, we talk about a cycle. What do you want to know about the engine? Of course, I want to know how much mechanical work I can generate out of the engine. So we want to find W cycle per unit mass. How do you look for W cycle per unit mass? You just combine the W from each step. So we can start from 4 to 1, and next one is 1 to 2, and next one is 2 to 3, and the next one is 3 to 4. Okay, and then leave the signs later. Let's take a look. W4 to 1 per unit mass, what is that? That is 0, so we can't get rid of it. The next one, 1 to 2. What is 1 to 2? 1 to 2 is an expansion process. Expansion process, that means the gas will expand and push up the piston. So your system, the gas, will generate work. If the system generates work, the work must be positive. So the sign should be positive. The next one, 223. W223 per unit mass is 0. Get rid of it. And then last one, W324. W324 is isentropic compression process. So that means you compress the gas. So if the gas gets compressed, that means the gas consumes work. If the system consumes work, the work should be negative. So that's why the sign here should be negative. Be careful here. Okay, should be negative here. All right, so what is left is 122 and 324. And we do have an expression for each one of them. 122 is U1. Oh, before that, let me just clear up. Is W122 per unit mass minus W324 per unit mass. And for 122, that is U1 minus U2. And for 324 is U4 minus U3. We derived those earlier. Okay, another thing we can talk about is, let's recall on a P versus nu diagram. If you have a P versus nu diagram, like the one you are seeing on the left, the area under the curve tells you work per unit mass. Okay, so now we can actually rewrite W122 per unit mass into area because work per unit mass is equal to area under the curve 122 and minus the second term W324 per unit mass, that is the area under 324. This has to be on a P versus nu diagram. So now let's take a look. Area under 122 minus area under 324. What is left? Area under 122 minus area under 324. So the only area that is left is, it's very easy from geometry. It must be the area of the enclosure. So what does the area of the enclosure actually tell you? Area of the enclosure is actually equal to W cycle per unit mass. This is what it says. Okay. All right. So we can make a note here. Area of the enclosure is actually equal to W cycle per unit mass. We just proved it. Okay, so after W cycle per unit mass, we want to know how much do I have to pay? What do you have to pay? You have to pay for the heat, which is QH over M. Which step is QH? Gaining heat. Heat addition process. That must be the combustion, which is 4 to 1. And we derive the equation that is U1 minus U4. This is how much you have to pay. So now, after I find what I get, W cycle, and what I pay, QH, the next question is, what is the efficiency? Efficiency is defined what you get divided by what I pay. What I get is W cycle. What I pay is Q4 to 1. So we divide both of them by mass, and we derived the expression for both the numerator and the denominator. For the numerator, it's U1 minus U2 minus U4 minus U3. And for the denominator, the solution is U1 minus U4. We rearrange that. The solution is 1 minus U2 minus U3 divided by U1 minus U4. And now, just like we said before, you can see the key to solving any Otto cycle question is to look for the lowercase u of every single point. Just like when we were at the vapor power system, the key was to look for lowercase h of every single point. Okay, so now let's introduce a new parameter. This is called compression ratio. Compression ratio is really important. It has direct connection with the efficiency. We use letter gamma for compression ratio. The definition of gamma is actually very straightforward. That is biggest volume during this cycle divided by the smallest volume in this cycle. Okay, let's take a look. Which point has the biggest volume and which point has the smallest volume? Let's take a look at our P versus nu diagram. So now can you find which point has the highest volume? In other words, which point has the highest x coordinate? It's very easy. It's either point 0.2 or point 0.2 or point 0.3. Doesn't matter because it's a vertical line. And then which point has the smallest volume? Or in other words, which point has the smallest x coordinate? It's point 0.1 or point 0.4. Doesn't matter which one because it is a vertical line. So now let's go back to the definition. The biggest volume is V2. You can also say V3. The smallest volume is V1. You can also see V4. And then divide both of terms by mass, so it becomes nu2 over nu1. And make a note, nu2 is equal to nu3, and nu1 is equal to nu4. When do you have nu2? When do you have the biggest volume? When a piston is at the bottom dead center. The bottom, the lowest it can go. When can you have the smallest volume? That's when the piston is at the top. We call it top dead center. Okay, and then we introduce a few new equations. If the process is isentropic and the substance you have is ideal gas, then you can have the following equations. So out of the four steps, which steps actually satisfy those two requirements, isentropic and ideal gas? So first of all, ideal gas. Every step satisfies ideal gas. And then isentropic, which steps are isentropic? There are only two steps, 1 to 2 and 3 to 4. This is the first equation. Second one, between 3 and 4. Okay, so those are the two equations you can use, and K, just like before, is the ratio of the two specific heats. The value of K is equal to 1.4 if the substance is air. And then one last equation, efficiency eta can be calculated from this equation. 1 minus 1 over gamma K minus 1. Those are the equations you can use for process 1 to 2 or 3 to 4. Okay, let's take a look. Gamma is our compression ratio. How does gamma affect our efficiency? If gamma goes up, if you have a really high compression ratio gamma, what's going to happen to the denominator? The denominator here will just become bigger. So the second term will just become smaller. 1 minus something smaller. So your solution will become bigger. So our conclusion is, if you have a high compression ratio, your efficiency will also be high. So that's why when you purchase an gas engine, you want to look for a high compression ratio. The higher the compression ratio is, the higher the efficiency will be.